So welcome everybody. Sorry about that little delay, but I think I'll try and catch up. It's just a couple of minutes. Let me start off by introducing myself. My name is Adarsh Pannu, and I'm an STSM with the IBM Analytics platform. Basically what that means is that I'm an engineer and I write code. That's my day job. And I've been working with the Hadoop and Spark stack for a little while now. So I'm really happy to talk to you about Apache Spark today. So we have an hour. The material I have usually needs half a day. So I'm going to compress it. And I'll give you pointers as to where to go after this presentation. So for today, or for this hour, I'm going to do a 20,000-foot view of Spark, just a very quick overview. We will dig quickly into the Spark stack. I want to show you Spark in action. I really want to make it real for you. I presume that many of you have already seen a lot of marketing slides and all of that, and you don't want to do that again. So I want to actually make it concrete for you. We will talk about Spark and MapReduce, and ultimately we'll end with what IBM is doing, with Apache Spark. So a little bit of history as to how we got here. So 2009, there's this young UC Berkeley grad, Matej Zaharia. He's actually gone on to get his PhD and is now a professor at MIT. So he started this project, and it's been 6 years, since this has been in development. And Spark has seen a phenomenal rise. It's actually the most active open source project right now out there. So within the 6 years, we've now added collectively in the community 7 components and counting. We have a lot of components which are outside of the Spark code base itself. These are third-party packages. We've had about 500 plus contributors on the stack. And that's 500 million lines of code, right? So 400,000 lines of Scala code. Now, I just want to mention that I actually downloaded all of the Hadoop components, or at least most of them, and I counted how many lines they were, and that came out to 17 million, right? So you may say, gee, this is like fairly small, but given that this is Scala, you can multiply that by 10, right? So roughly 4 million. So even though Spark has been rapidly growing, it's still fairly small, right? But as I say, small is beautiful, and Spark is certainly beautiful, and you will see why. So moving on, despite all of the progress that has been made on the on the code base, it's still one platform, right? It's a cohesive platform. It's not 15 different products. It's actually one product, and so much so, and the capabilities are so rich that if you've been to some of the keynotes of our executives, they actually call it the analytics operating system, right? So Beth Smith did a keynote at a Spark Summit, I believe, earlier in the year, and this very moment, one of our executives, Anjul, is speaking at the Spark Summit in Europe, and these are some of their slides, right? They call it the analytics operating system. So my goal, I feel, is to make this real for you. I want you to know why we call it the analytics operating system, more than just a sound bite. And so hopefully we'll achieve that in this hour. So I pulled up the big data dictionary, right? There is such a dictionary. And I saw this definition, okay, of what Spark is. So, and this also tells you what it is not, right? So Spark is a general purpose compute engine. It's a data processing engine, right? It's general purpose because it is not meant for one specific job, say sorting or anything else. You can express a wide variety of applications on it. So it's a general purpose compute engine. It's not everything, it's a compute engine. So you bring your own data is basically what Spark is, right? It is also a technology that does not replace Hadoop. It works well with Hadoop, right? So this is one of the myths out there that I've seen expressed. As an engineer, it kind of is appalling to me to see that there's this confusion going around about Spark and Hadoop. They actually coexist and work beautifully, right? So it's not really a replacement for Hadoop. It interoperates with Hadoop. And lastly, starting from the first 10, 20,000 lines of code to 400,000 and beyond, it's becoming an ecosystem. Why? Because third-party packages are coming in, applications are coming in, products are coming in, and pretty soon we are going to find that the code base built on the Spark engine is going to exceed Spark itself. So it's going to flourish into a very nice, beautiful system with a whole range of tools. So if you walked out of this presentation, right, and this is just one takeaway, right, a high-level takeaway from a business point of view as to why you care about Spark, it's just two things, right? And sure, when you listen to people, they'll say, hey, Spark is an in-memory database. Okay, it's not. Or they'll say, hey, Spark uses JVM really in a very cool fashion. But ultimately, it's none of those things. It's a very expressive system, and it's very fast. Okay. So let's talk about expressiveness. What I mean by expressiveness is the functional vocabulary, right, of the system and the range of problems that it wants that you can solve with it. So it's really expressive in that sense. It has a very rich set of APIs which we're going to go through, and of course it's also very productive. Some of that comes from the fact that it uses languages such as Scala and Python, and it uses them in ways that improve developer productivity. Now, functionality without performance is useless to us. We know that, right? I mean, we have lots of cool systems, but we want them to be fast. And Spark, for sure, is very fast. Okay, a common comparison point that people like to give out there is this 100x, right? Now, as an engineer, let me tell you that don't worry about the 100x right now, because that usually is the number that you get when you're running specific in-memory applications that tend to be very iterative, more like machine learning applications. The number I have seen in our labs and in our benchmarking is more like the 2 to 10x. Okay, and I've seen the 3x number a lot, 3 times compared to Mac. I've seen that very often, mostly in batch jobs. So now you'd like to say, hey, it's only 3x. Heck, 3x is a lot, right? Even if you take some MapReduce applications and just implement them on Spark, you can expect to get about 3x. So that's what we've been seeing. So again, it's expressive and it's fast. So that's the 20,000 foot picture. Let's just go down to more like 2,000 feet, right? So even though it's one platform, as I've already mentioned, it comprises of 7 some components depending on how you count. Now the heart of Spark is what is called the Spark core. This is really where more than half of the code is actually in Spark core. So this is not just some engine which can't be usable. Actually, a lot of applications out there are written primarily on the Spark core. And the core is the piece of the engine that does your basic operations of data processing, filtering, mapping, and so on. So I think of the 400,000 lines of code, core was over 100,000 is when I counted, so it's about 1/4. But it's fairly stable. It's the piece that's been around the longest. You can build applications on top of it, and they're going to run fine. Now, building on the core are these other high-value components, primarily for data at rest, which would be Spark SQL, MLlib for machine learning, and GraphX for graph processing. I'm going to explain to you exactly what these are, so when you walk out, you know exactly what each of these are. And of course, for data in motion, there's Spark Streaming. There are some other auxiliary components like data frames and ML pipelines that kind of go hand in hand with SQL and MLlib respectively. So I'm not going to delve too much into that right now. So that's your basic stack. Capabilities of this stack are available through 4 languages. Spark itself was written in Scala, a JVM-based language. So that obviously is a language where all of Spark capabilities are available. And similarly, Java is the same way. So I would say amongst equals, Scala and Java are more equal. Okay. Python is also a language that is supported. It tends to lag a little bit in terms of functionality and performance, because it's not a so-called first-class language. You will see a difference, right, in terms of performance. Sometimes you might see a difference. And R is the one which is the newest, but that's also where a lot of work is going on. We at IBM are also helping improve the Spark R piece. Now, I didn't mention that Spark is basically bring your own data. Okay, it doesn't provide you any data management capabilities. It'll work with data you have wherever that is. So it'll naturally work with HDFS. If your data is in a Hadoop system, a Hadoop file system, Spark will run off of that. But your data could be in a SQL engine somewhere, or it could be in any of the NoSQL products out there, and Spark will just run with it and compute it and crunch it and so on. You might need to write an adapter, although there are tons of adapters already available out there. So this is the high level, I called it the 2,000-foot view. Okay, before we drill into it, there was an exercise. So all of you are here because you're trying to figure out how to use Spark in your businesses. There was an exercise I started doing earlier this year where I went to the websites of all the conferences, the 4 or 5 Spark Summit conferences, the Hadoop World, Hadoop Summits, and several others. And I started cataloging use cases, right, by industry, by verticals, and horizontal capabilities. And I started putting together a spreadsheet, but I can't show that to you because it has names of companies and stuff, right? The only thing I can show you, or I can tell you, is that I found a wide range of industries already represented in that spreadsheet that I'm making. And you can name pretty much any combination. Like, for example, I know of use cases in media and streaming, Netflix, right? I can name that. Or media and machine learning, Comcast, they're doing recommendation engines. I can name banking and financial services with wrangling, or even graph processing. So suffice to say, you're here because you want to figure out how to use Spark. This is just one of the many presentations you will attend, but please go out to the internet and you will find use cases which are very similar to what you want to do, and you can learn from that. And of course, come back to us, right? We have a lot of experience with Spark now, so as IBMers, we are certainly happy to help you. Okay, so that's the high level business value. Now, coming back to my engineering hat, right? Hey, at the end of the day, Spark is just a collection of APIs, okay? Now when they asked me to do this presentation, I told them, listen, it's going to be an engineering-oriented view, right? So I want to make Spark real for you once again. It's a collection of APIs. I want to show you those APIs and build a story for you around a data set that some of you may already have been familiar with. This is a data set which actually, unfortunately, has been beaten to death in the data science community. It's called the on-time airline data set. I have used it in several presentations, so I'm going to just beat it to death once again. So what this data set is it's a record of every flight in the US that was scheduled over the last 25 some years. Okay, so it's millions of records, and each record looks like this. So pretty much, when was a flight scheduled? So in this case, it's Continental 65 in 2004, Feb 5th, and it was going from, say, EWR, which is Newark, to Los Angeles, and was going to fly a distance of 2,500 some miles and so on. So a lot of other metadata. So what I'll do for you is I'm going to use this data set, and let's build an application. It's not a live demo, but let's build an application. I'll take you through the entire stack. So when you walk off of this place, you know what can be done, okay? So let's ask a simple question. Now, so what's the measure of an analytics platform is the kind of questions you can ask of it, and how fast does it get back answers, right? So we're going to ask a bunch of questions to Spark using this data set, and I'll run you through the stack. So the first question is very simple. Which airports had the most cancellations? Actually, I wanted to know this because it's a real world data set. There's some airports I always get stuck at, and you probably know what they are. So I said, let's compute this using Spark Core, right? Just the core API. So, you know, if you were 10-year-olds, right? Actually, today 10-year-olds are pretty smart. Some of them are writing code, right? So how would we design an algorithm to go about figuring out which airports had the most cancellations using Spark Core? So we would start off with row at a time, right? This row has 29 fields, and we are only interested in 2 fields, the airport code and the cancellation code. So I conveniently picked 4 airports, actually 3 airports, and I very conveniently picked records where the flights were canceled, right? So Newark, there was a flight canceled. Honolulu, it wasn't canceled. And Chicago had 2 flights canceled, okay? So I extracted from the 39 fields using Spark, I got down to 2 fields. And then I want to throw away Honolulu because that flight was not canceled. So I'm only interested in canceled airports, right? So it leaves me with these 3 records. And what do I want to do now? I really want to do a grouping, and I want to do a count. So all the Chicago has to come together, and the Newark has to come together, right? A 10-year-old would do that. And so we do the same thing. So we end up with EWR of 1 and Chicago of 2. And now we are interested in sorting this to make sure that the most cancellations come at the top. And so we end up doing a sort. And now we have these 2 records. We started with millions of records, but we may end up with as many as there are airports, I suppose, right, in the United States. And eventually we are ready to return data to the client. So you see how it's really simple. A 10-year-old would write it very simply. Now in Spark, we would write it just like that, like I said it, okay? That's Scala code. Many of you here may not be developers or programmers, and if you are, you may not be familiar with Scala, but don't let that worry you. What I'm trying to get at here is see the expressiveness. I had 6 steps in my mind, and I expressed that in 6 steps in Spark, okay? If I were to just remove all the crud and show you just the lines, that is what those lines are, and they actually mean what I say, okay? So I did. So you can try this at home. If you try this on MapReduce, you're going to get, I think, 2 jobs. I'm guessing. I haven't tried it. You're going to get 2 jobs and hundreds of lines of code. Much of it would be boilerplate, and it'll be hard to manage and maintain, okay? So it goes back to the expressiveness. Okay, we're not done. This was just the first question we asked. Oh, by the way, you want to know the answer, right? So I ran this on a small subset. I only ran this on the 2008 year. Can you guess like what the highest airport would be? O'Hare? There you go. Yeah. So Chicago, Atlanta, Dallas, LaGuardia, and Newark, those round out the top 5. So this data is actually pretty cool. I was able to do a lot of other analytics with it using Spark and, of course, using R earlier, where I can figure out, how do delays rack up in the day, and not just which airports are bad, but a lot of other cool statistics. So if you are delving into Spark, after this presentation, you want to go off and write some code, use this data set, right? It's real world, and it'll give you really cool insights. Okay. So yeah, we're not surprised. So moving on. Now, so we were at what, 200 feet or ground level? So for the next 2 slides, let's go underground because that is where the rubber hits the road, right? You need to know the stuff for you to really know what Spark does and why it competes with MapReduce. So I showed you 6 steps, didn't I, right, to write this little application. As it turns out, when you run it on Spark, Spark basically takes those steps and builds a data pipeline or a DAG, right? A DAG is a directed, in CS parlance, we call it directed acyclic graphs, right? They're graphs, and they flow in one direction. So Spark builds a DAG, and for that 6 steps, it basically built a DAG which had roughly 6 steps. Now, these steps or nodes are called RDDs, and you have to know what an RDD is. If you've been to a Spark presentation, you have to know what an RDD is, because that's what people talk about out there, okay? An RDD, guys, is nothing but a node in a graph. So when you build a data pipeline, the pipeline is built of these steps. Start with a Hadoop file, I extract 2 columns, I reject the rows I don't want, I group, I sort, and I collect. So those steps are RDDs. But they're actually more than just those nodes, right? They're more than steps. Ultimately, an RDD, what it represents, being a node in a graph, it represents a collection of data, right? A collection of records. It could be a collection of objects. It could be a collection of anything you want, but it's a collection. And in Spark, these RDDs or collections are broken up. They're partitioned, and these partitions could rely on multiple nodes of a cluster. So RDDs have little pieces, and they sit on different nodes of a cluster, which means that if you break something up, you can work on it in parallel, and that's the whole idea of an RDD, to break it up into partitions. Now, intuitively, you know that some RDDs which are sitting right on top of your data, the Hadoop file system or Cassandra or SQL or whatever, those are RDDs that are kind of working off of materialized data, right? Because the data is right there. And then there are some RDDs way up here, like for example, the RDD that represents all your canceled flights, or the RDD even before that that represents all the airports with the most cancellations. Those also represent data. And the data there is actually not necessarily materialized. It's computed on the fly, right? But they're RDDs no less. So what I'm getting at here is RDDs, they stitch together to form these data pipelines or DAGs, and they can be parallelized, and because they have their independent identity, they could be cached separately, and they could be recovered from, you could recover them from failures. So the architecture, the way, you know, the guy, Mate, has designed it, this encapsulation lends itself to so many benefits around caching, recovery, and so on. Just one more slide underground, and then we will go back up. So I described how Spark takes your 6 lines and builds this data pipeline. Spark actually goes a step further and says, you know, this data pipeline, how do I break it up into pieces so that I can run some RDDs together? RDDs where data is just merely flowing through a pipe and doesn't need to come together from other machines. Spark breaks those into what are called stages. And Spark runs stages at a time, and each stage can contain some number of nodes. So in this example, our application is trying to figure out, start with the rows, extract 2 columns, and filter out the flights which are canceled. These steps can be done in one shot on the same partition on the same machine. So Spark calls that a stage, and it runs these RDDs together. But then we have a problem, right? Now we are sitting with EWR on one machine and EWR on another machine, and we need to bring them together. And so the only way to do that is to shuffle data, right, across machines. So there's that process called shuffle that happens. And at the end of the shuffle, the next stage can start, and so on, and you can build any number of these stages until you're ready to return data to the client. So some of you may be thinking, heck, this is MapReduce, right? MapReduce basically does the same thing. So why is Spark different, okay? And the reason Spark is different is actually quite a few reasons. The first comes to just the vocabulary, right? When I talk about expressiveness, MapReduce is like Morse code, right? You can say did da, and all of that, okay? And map is did, and da is like reduce. And sure, people can argue that you can express a lot with did, does, but Spark is like the alphabet. So you have 2 operators versus you have a rich set of operators. In MapReduce, you basically can stitch only map and reduce, and then you have to fall back to HDFS to materialize your data. So if you have a complex job, you can write MapReduce, 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 and stitch them together. So it's just not expressive. Spark, once again, has a very rich, you can form very rich data pipelines, so one application pretty much. There are other significant differences. In Spark, each map and reduce is like one heavyweight Java virtual machine task. But in Spark, we use threads inside a JVM, so these tasks can like come in and go really rapidly, and that lends a lot to the speed. Additionally, Spark can exploit memory and your local disks in ways that MapReduce doesn't. So I mentioned caching, and I'm going to describe that in the next slide. And I also mentioned shuffle. Some of those components use memory and disk in very clever ways, which add to the 3x to the 100x speedup that I talked about. There are other innovations that have gone into Spark around how fast the shuffle is and so on. They all lend to speed, so we don't have to go into the details. But at a high level, this is really the difference between MR and Apache Spark. I have talked about expressiveness a lot, and I've talked about this vocabulary, and we talked about MapReduce having map and reduce. Now Spark, of course, has map and reduce. What these are, once again, are operations, but these are also loosely, you can think of them as RDDs themselves, right? And operations and RDDs are kind of more or less one and the same thing. So Spark has not just map and reduce, but it has flat map, join, union, sorting, disting, sampling, intersection, and many more that I can't list. The API is really rich. And you will immediately notice that these are basically your very rich functional and relational APIs, right? You can actually build a database engine off of these APIs, and Spark has actually just done that. On top of that, Spark also has these things called actions. Once you've built your RDD graphs, what do you want to do with the data that flows off of the top? You want to write it to disk, maybe. You want to get it to the client. You want to get the first 10 rows. You want to sample it. So it also has a rich collection of actions that you can take on RDDs. So the expressiveness of Spark comes from basically this slide. And this is only Spark core. So I'm describing basically 1/5 of the stack at the moment. Okay, when we go into the rest of the pieces, you will see there are more APIs. One last slide before we go on to our application, which I promise I'm going to run you through. So here is our RDD DAG once again that we just formed with our application. I apologize, I kind of twisted it down. So in this case, data is flowing from the bottom to the top as opposed to the other way around. But either way, what I want to mention to you is that any of the nodes in RDD DAG could be cached. I could just say cache this in memory or persist it on disk. And so from that time on, if you have applications which are repeatedly computing the same results, they do not have to suffer the CPU cost or the IO costs involved. So what I've shown in this example is that, let's say the RDD which filters out only the cancelled flights, I could have gone in my application and said cache this, and all of the other jobs on top didn't have to recompute the cancelled flights because it was done once. The entire data, how many gigabytes, terabytes, would have been scanned once, and it would have been aggregated down into that one green node. So, so this is how Spark can exploit memory if you have it. Now this has also led to a myth. Okay, this has actually led to several myths about Spark, and as an engineer, I see these fairly often. Okay, so the first myth is that I've actually had people tell me that, hey, I can't use Spark because I don't have like 20 terabytes of memory. Okay, and you don't need 20 terabytes of memory actually if your application doesn't need it. So Spark does not require you to load all your data in memory. Okay, it'll use the memory you have, especially if the application tends to be iterative and recursive, but you don't need it. We've already covered number 2. Spark is not a replacement for Hadoop, so it's just a myth. It's a replacement for MapReduce, and we'll talk about that some more. The third one is people think it's only for machine learning, and that only came about because the first application of Spark was machine learning. Machine learning, you know, ML, we do optimizations and we do convergence of functions. We run the same code again and again over the same data. So Spark is a very good use case, but not just ML. And lastly, if you're here for the last point, I'm sorry, right? Spark doesn't really help us with any of those things. Although some of the presentations make you feel like it does everything, right? There are many benchmarks out there around Spark and Hadoop MapReduce. If there's one that I could share with you, it would be this one. Okay, I think it's called the Daytona sort. It's out there on the public domain. So in 2013, the winner of this benchmark was Hadoop. Yahoo did this. with 2,000 some machines and 50,000 cores, and they took about an hour. This is a sorting benchmark. So this is really a benchmark on steroids, because sorting, as you know, doesn't reduce data sizes. The entire data flows through the cluster. So it's actually a very good benchmark. Spark, the first time, they took like 1/10 of the machines. This was last year. 1/10 of the machines, and this is on the public cloud. This is not even like real hardware. It's on the public cloud. And 1/7 of the cores and 1/3 of the time. Okay, so this is a purely batch application, right? And so you can see the 3x speed up that I talked about, they saw the same thing. They went ahead and sorted 1 petabyte, which is I guess 10 times, and roughly 10 times the time as well, and they proved the scaling of the system. So of all the benchmarks out there, file this one away in your mind, right? When somebody talks to you about MR and Spark, right? This is the one you want to use. Okay, so let's get back to the application that I promised we will, look at, and I need to speed up it a little bit here. So the question once again was, we said which airports had the most cancellations, and I wrote 6 lines of Scala, and you may say, heck, I don't have people who know Scala. I don't want to write Scala. I mean, I probably don't want to write Python either. So then the obvious question is, can I compute this using SQL, right? Lingua franca of database systems, right? Many of us know SQL. And the answer is yes. But the bigger question is, can I use SQL without leaving my Spark environment? Okay, there are tons of SQL engines out there. Heck, we have a very good SQL engine called Big SQL. You could certainly use that. But what if I don't want to leave my environment, right? I want to do a mix of Scala, mix of SQL. Can I do that? Absolutely. And that's one of the selling points of Spark, okay, this interoperability. So I will show you some code. Only look at the colors, right? We have already established that you can create an RDD out of any data out there, right? I can create an RDD out of a file system on Hadoop. I can then take the next step and give that RDD a schema, and that gives me something called a data frame in Spark. And data frames can then be queryable by SQL. So if I register that data frame with the Spark system, I can write that query, okay? So I can say, select origin, and I do a count, group by origin, where the cancellation is 1. So that's actually not 3 lines, that's 4 lines, because the order by is kind of stuck in there. So I went from 6 lines of Scala code to 4 lines of SQL. And I can do a lot more SQL going forward. And this is actually a very, we are seeing this paradigm a lot, right? A lot of our customers may not want to use RDD core. They may just want to use SQL to build the same structures. You're ultimately still building RDD DAGs. You're just using SQL. So let's just describe what Spark SQL is. It's a SQL engine in the Spark stack built on top of the core. It has a teeny little optimizer, but it's not meant to be a full-fledged SQL engine like our Big SQL. Okay, it's ultimately the primary goal of this is to write less code for many cases. But if you have some TPC DS with 2 fact tables and 100 dimensions and major snowflakes going on, this is not for you. But if you have relatively straightforward things, then you can use Spark SQL. There's also a secondary goal, which is, I mentioned early on that Python is not quite a first-class language, although some of the Spark developers may kill me for saying that. I don't think it's a first-class language yet, right? Because the system is written in Scala. So if you're using Python against the core, there is that performance penalty that I described. But if you're using SQL, then that penalty goes away. So that's the second kind of benefit of using Spark SQL. Okay, so we've asked the same question 2 different ways. But now, to my analytics platform, let me ask a slightly different question, right? So I know what flights are delayed, what airports are sucky, right? I know that already. But can you tell me which flights are likely to be delayed? Can you build a predictive model for me? Right? That's the question I want to ask. and I want to ask that of the same data set. I want to really figure out, build me a model to predict flight delays based on whatever features I throw in. And so can we do this in Spark? Yes, of course. And once again, the bigger question is, can I do this without leaving the environment that I'm just putting together for you, right? In the environment that I'm still sitting? And the answer is still yes. And the way you do that is through some more code. Only focus on the colors, right? So I'm going to, so let me run you through this. So let's say I'm a data scientist and I'm saying, gee, I want to build a model to predict arrival delays, the first column in my SQL query there. And I feel that arrival delays tend to happen because of maybe departure delays. I guess if the plane was late at the gate leaving, then it's going to be late at the gate arriving. Okay, so that's conjecture. I would throw that in as a feature. I would also say, arrival time, maybe flights which take off and land later in the day, I already know that they tend to get delayed. So I'm going to throw that as a second feature, arrival time. Departure time kind of goes with arrival time. I'll throw that into the mix as well. And I'm going to throw in distance, just for good measure, thinking that, these airlines are kind of funny. I see that even though when you're late, the pilot comes on and he says, I'm going to catch it up, I'm going to speed up the plane or whatever, right? So, so I'm guessing that distance, if you have a longer distance of flight, that might have some bearing on the pilot doing these clever things. So I throw in 5 features and I'm predicting arrival delay. So I conveniently used Spark SQL now, not core. I use Spark SQL to build my so-called training set, which has only 5 columns in it, right? The 5 columns that I just mentioned. And then, so I built the training set, and then I used an algorithm called a decision tree. I used it in regression mode, and I ran it on the training set, and that line just builds the model for me. Okay, and after that line, I have the model which predicts arrival delay based on those 4 other predictors. I can then go on and use Spark Core and RDDs, and I can actually evaluate my model, and I can see, because I have the real data, I can see how my model compared to what is in the data. And I can do that using those 3 lines of code. So all of this, you noticed I have not left my application environment. I'm just mixing and matching rich functionality. I don't have to walk out to R or some other system to do this. It's within, right? Within your environment itself. Okay. Yeah, so to reiterate, there is a very tight interoperability happening between RDDs and data frames and MLlib operations. You can seamlessly glue them together. So let's just step back up and now describe what MLlib is. So it's, as we know, already a component of the stack with the express goal of making scalable machine learning. The keyword there is scalable, because you can do machine learning in R, but it's like on your laptop, right? And you can't run it on terabytes of data. So scalable machine learning. In the open source community, we started off by adding a whole collection of algorithms. So you can do L1, L2 regression, you can do classification using support vector machines or decision trees, k-means clustering, ALS recommendation engines, frequent item sets, and a whole set. So the collection of algorithms is growing. But we know that algorithms is not all that is needed in an ML system. An ML system is more than a collection of algorithms, right? As I showed you in the previous slide, there is a method to the machine learning madness. There is a way you go by building training sets and building models and evaluating models and so on. And that whole pipeline is very important. So in Spark, we have a component called ML pipelines, which facilitates not just the algorithm usage, but the entire workflow. So that was one of the boxes that you saw on the chart. And lastly, at IBM, we have very strong expertise in many areas of data management. We obviously are SQL experts. We also happen to be machine learning experts in our Almaden and Watson labs. In Almaden, our researchers created a system called System ML. Very loosely, what that is SQL for machine learning. just as you have SQL or relational databases, this is SQL for machine learning. So you don't want to be writing low-level Scala code or low-level JVM code when you can write at a higher level, at a level that data scientists really want to write at. So SystemML radically simplifies algorithm development because you don't have to drop down to the gory guts of Spark necessarily. And we recently contributed this to the open source community, and we are working very aggressively with the Spark community to fold our IP into the Spark stack. So pretty soon, actually by this time next year, I may have another box next to MLlib, or actually it may just be MLlib with SystemML IP. We're trying to figure out the exact dynamics there. Okay, moving on to our application, right? So talking about the different types of questions that you can ask the system, I'm going to now ask another question of our system, okay? This is a little tricky one. I have this data, airline data, records at a time. I want to figure out what's the shortest way for me to go from Maui to my daughter in Ithaca, okay? So how do I figure this out? This is a graph query, right? This is not a row at a time. This is a query that needs you to hop between cities to figure out what the shortest path is. Don't try this on a relational engine, okay? Because it will not scale. I know it will not scale. I've spent many years on relational databases. So now, can Spark help with this graph query? And the answer is, you get the drift now. It can, right? And once again, right, can I just do this seamlessly within the same environment? And the answer again is yes. And I'm not going to show you code for this one. Instead, I'll show you a pretty picture. So what I really want as a developer on Spark is I want my data that looks like rows and columns. I want it to look like this, right? And I want to operate on this structure so that I can get the answers I'm looking for. So in Spark, I could actually turn this data that I talked about into a schedule graph. I could actually do that, where your nodes or your vertices in the graph are cities, right? Maui and San Jose and Ithaca and so on. And your edges become flights. So I can actually build this. And I can write algorithms which allow me to figure that out. Okay, so that's the answer I'm looking for. And GraphX allows me to run this kind of queries. It's not something you can do easily on most systems, especially when those systems also do data processing and machine learning and streaming. Okay. So what is GraphX? To repeat, it allows you to turn your RDDs into property graphs, which are nothing but collections of vertices and edges. And it gives me APIs so I can slice and dice this graph. I can take subgraphs. I may only be interested in, say, flights originating from Chicago or flights coming into Newark. So I could do those subgraphs. I could also write algorithms which compute these distances. So for instance, I could say that the shortest flight for me could be based on maybe distance, or it could be based on time, it could be based on layovers. Any of those things I can actually encode and not leave my environment, right? It's all in the same ecosystem. So Spark gives me multiple views. You see how of the same data. I actually, unfortunately, haven't gotten down to writing the code for this. Maybe next year I will have a slide for you. Okay, so on the theme of asking questions, let's take a twist and ask a slightly different question, okay? So far, we had the data sit nicely partitioned and sitting on HDFS. But of course, this data comes from, systems which are collecting this data in real time and actually aggregating it together. Right this moment, we know we have hundreds of flights in the sky, which are generating some of the data that was used and aggregated, okay? And we know that there are websites like flightaware.com and others which use this data. So my question is, okay, that's not the question. Okay. So the question is there a way that I could use Spark not just for this data at rest, but for this new data that I'm defining for you that's coming across a streaming interface. And maybe I can start correlating that streaming data with historical data, or I could start running queries on this streaming data. So Spark absolutely allows you to do that. And you do not have to leave the system, okay? Once again, it's all in there, guys. It's all in there. And on streaming, the way it does it is really through a method called microbatching. If you are interested in streaming, you need to know this. So all Spark does is that it can read data from these data sources like a Twitter firehose or a Kafka stream or whatever, and it takes this data and presents that to the rest of the system as RDDs, okay? It micro batches the data coming in, and these batches are created based on time windows. Could be milliseconds, seconds, and so on, right? 5 seconds, anything. And so it creates these RDDs, and guess what? When I give you an RDD, then you can run anything on it, no? You can run Core on it, you can run SQL on it, you can run MLlib on it. So that's Spark's bridge, you know, for streaming data. It presents streaming data also as RDDs, and therefore seamlessly opens the rest of the system to you. So once again, all inside the same environment. If you think I'm getting excited, actually I am. Whenever I give this presentation, it just warms my heart knowing that this guy created such a beautiful system, right, where it can do so much. Yeah, you have a question? So yes, so the question is, am I using Hadoop at that time? And maybe this slide will help you, right? I'll use a slide to answer that question. So, so the answer is yes or no, whatever you want, but I'll go into the detail, right? So a sample scenario, right? It is totally conceivable that in your business, an architecture is created where you're using Spark to read data from Hadoop and HBase. You are dropping into Core, and SQL and MLlib, you're interchanging them, maybe you're building models, and then you have some data in the enterprise which is coming off the wire, and you're deploying those same models in another Spark application using streaming, and perhaps when you score that model, you're writing the results back to Hadoop. Okay, this is a very viable architecture, and I've seen this in many places. Okay, we come full circle, don't we? Right? You know, really, hopefully I've showed you how this one platform, right, is really your analytics operating system. You know, you can do a lot with it, and this is the reason why our executives, you know, like to use that tagline. You know, it is our analytics operating system. I have about 10 minutes left, so let me just go on real quick. Hadoop and Spark, this theme comes again and again, and I have to repeat this in this presentation too, because I just want to kill this myth about Spark replacing Hadoop. So Hadoop is a collection of many, many components, but at its core, it's a three-pronged pedestal, right? It's storage, it's cluster management, and it's compute. Okay. Spark doesn't bring storage, and Spark doesn't bring cluster management. There is something called a standalone Spark cluster, but that's not really a robust system for production. So with Spark, you need storage, some form of storage, and you need cluster management. We recommend HDFS on Big Insights, and we recommend Yarn on Big Insights. And Spark is a replacement for MapReduce. Now the thing is, many of you may already have MapReduce in your businesses. If those applications are working fine, don't touch them. But maybe they're not working fine. Maybe you could shorten them and use that hardware and resources for something else. So absolutely look at Spark and see if you can, you know, port those things to MapReduce. Moving from MapReduce to Spark is not that complicated. It's actually fairly straightforward. And you will have like much fewer lines of code, maybe like 1/5 the lines of code as well. So it'll help you even in maintenance. At IBM, the approach we are taking a three-pronged approach again. So we're actually we have doubled down, we've like tripled down on Spark. We think this is the technology on which the next generation of analytics engines and solutions will be built. So we have created a Spark Technology Center out of San Francisco, and we have a few dozen engineers there, people like me, and I work closely with those guys who are contributing to the Spark code base itself and enhancing it. Of course, we ship Spark with Big Insights, and we also have Spark available as a service out there on the cloud. And lastly, we are using Spark within our own products. So I know at least a dozen products, real products inside IBM, where we are actively either looking at Spark or would be integrating Spark in, and maybe over 100 research and other experimental projects. So the scope is vast. Even in this conference today, I was counting, we have 50-some Spark presentations. So that tells you the commitment that IBM is making, towards this technology. I want to leave just a few minutes for questions. So this is a description of STC. I've already kind of mentioned this. This is a description of the work we're doing with Spark internally. I don't have time to go into it, but I think that these slides are on the internet, okay? What I do want to get to real quick before I close is that some of you may want to learn more about Spark. This is just an hour. I actually put out a whole bunch of slides. I call them reference slides. Let me just give you a preview. So I've built out a pathway for people who want to learn Spark, right? And these are like black, starting from green belts to blue and red and black belts, okay? And I've estimated the amount of time you might need, and I have a whole bunch of references here as to what you should go through, right? What you should read, and what papers and books and conferences and so on. So I'm not going to go through this. Yes, this is self-study. Well, if you're working with open source, then maybe we don't go to formal classes, we just self-study, right? So please take a look at that. And other than that, I have to show you these two slides, disclaimers. And thank you so much. I have about 5 minutes and I can take some questions, yeah. So the question is, do I consider Spark a graph database? And if not, what's the difference? So I will confess, my background is in data management. I'm not a graph expert. Having said that, I have been told that Spark, much as even Spark streaming for streaming, brings you 90% of the way for many graph applications, right? But is it a full-fledged graph database with storage and all of that? Probably not. We have people in STC who would be able to answer that question if you want to reach out to me, but that's the best I can do at the moment on graph, yeah, okay. Okay, guess that's it. Thanks again. Yes, I think it should be the yeah, they are. They told me that all the slides are available as PDF. So I uploaded the PDFs last weekend. So yeah. Oh, you can't? So if you can't, send me a mail, and I'll just send you the PDF. Yeah, that's fine. Okay. Yeah, okay. Thank you.